So before we begin our experiment, it might be helpful to give a detailed explanation of what a meniscus is. A meniscus is this curve that might appear on the surface of a solution when placed in a container like a graduated cylinder or pipette. It occurs because, let's just say this is water. The water molecules will be attracted to the molecules that are in this wall. And because these molecules of the solution, the water, are attracted to each other and they have polar bonds, the water molecules will still be attached to these molecules that are attracted to the wall. So it'll just be higher near the walls, and then it'll fall towards the center. We read a meniscus by reading the bottom of the curve right here. So if we were reading from this one, we would set this at about 2.0. It's pretty on the line right there. So yeah, we'll give more examples in the experiment, but I figured that this might be helpful.
Alright, so now we transfer our 2% stock solution to another beaker using a pipette. Normally we would use a graduated pipette, but one wasn't available today, so we're just using a regular pipette. So you squeeze here, place it in the solution, let go, squeeze, and your solution is transferred.
Okay, you want to record your initial volume by reading the bottom of the meniscus, which is that little indent of water you can see. Right here it's at about 0.19. For your final volume, bring it to eye level, and right here it's at about 2.19 milliliters. And you can transfer that back
Now we're going to measure the mass of this to get the density. To fill the flask up the most accurately, we're going to get a pipette, and we are going to drop it up to the line. We're going to go to eye level and make sure that the meniscus is at the bottom. So there. And you have a filled up graduatus. Okay, now I'm going to pour all the stock solutions and diluted solutions out. And then I'm going to grab one of these brushes and put a little bit of soap in it and kind of, can we cut that part?
Just say that you just rinse it out really well.
Yeah. And squeeze that to kind of just get a little soap going.
Flip them upside down onto these dry paper towels. This data that we just collected, we need to use the dilution equation. This equation, initial volume times initial concentration, is equal to final volume times final concentration, compares an initial stock solution versus a diluted version of the solution. This just means that there's more added solvent to the dilution, but there's the same amount of solute. That's important, because if we have the same amount of solute, we can say that the concentration is equal to the amount of moles of the solute over the volume. This shows that concentration and volume have a direct relationship, meaning that if concentration or the volume were to increase, then the concentration would need to decrease, and vice versa. We can use this relationship to our own benefit, because we can, if we are given a known initial volume and a known initial concentration, we are able to change the final volume to whatever we want to find an unknown concentration. That would be a bit harder to calculate. So in our experiment, we measured an initial volume in our pipette of 0.19 milliliters and a final volume of 2.19 milliliters to get a total amount of volume delivered to 2 milliliters. So this would be our initial volume right here. And we would multiply that by our initial concentration, which we know because it was given to us, which is 20%. We used a volumetric flask of 25 milliliters. So this can be used as our final volume because we delivered additional solvent to our volume delivered to the exact mark. So we know we have exactly 25 milliliters. We can use this data to find the final concentration. So here we would just multiply 2 milliliters times 20%, not 0.2, 20% to give us a value of 40, and divide that by 25 milliliters. The milliliters units cancel out and leave us with concentration value of 1.6.